Hey guys, BuildZoid here, and today we're going to be taking a look at the Z390 Aorus master motherboard from Gigabyte. So, this is this is Gigabyte's second highest priced Z390 motherboard, and it kind of tries to do everything. So there's a lot of features on this thing. When it comes to, well, everything overclocking related. Gigabyte has other motherboards that, include some more like workstation oriented features, but this one's basically, if you want everything you need for overclocking, this pretty much has you covered. So let's get right into the sort of the features, and then into the VRM after that. Starting off with the dual 8-pin power situation. So basically, unless you're running some kind of exotic cooling system, you really don't need to worry about plugging in the second 8-pin over here. You just need to plug in this one. The system will run fine. It makes zero difference to plug this power connector in unless you can somehow cool more than 300 watts of CPU power consumption, which, due to the way the 9900K is manufactured, good luck. You're probably not going to manage that, and even then, 300, like even the low 300 watt range, you'll be more or less fine on a single 8-pin. It's really once you start talking about like X299, power consumption figures, that you start needing an extra power connector. So, yeah, it's just one of those things that I've seen a lot of people on the internet freaking out about, is like, oh my god, the motherboard has more power connectors than my power supply has. Well, you just need to plug in this one. You'll be fine, even with the 9900K. So that's that. Though, if your PSU does support plugging both of them in, you can do that, and it'll make absolutely no difference. Like, it'll certainly do no harm, but it's not like it'll actually give you any noticeable benefit. It might actually be measurable, but, if your equipment is sensitive enough, you can probably measure just about anything. So, yeah, but it's definitely not going to make a noticeable difference if you just run the single 8-pin. Anyway, moving on, up above the memory slots, and you can't see them, we have a bunch of voltage read points. So this is what I was saying about this board kind of tries to do everything. So it does have voltage read points, and as far as I'm aware, I think this might be the only motherboard from Gigabyte on Z390 where they have voltage read points. They are unfortunately just solder bumps in the PCB, so that makes them kind of a pain to probe. But unlike Asus, Asus likes to cram their solder points in stupid places, like, say, under your PCIe slots, so that if you have GPUs, you can't get to them. Or they put them right under the 24 pin, so when you plug the power cable in, you can't get to them. These are up by the memory slots, and I don't really like this is a good place, I think, to put them, because there's not really anything here that should be really blocking access to those. So that's a good decision. Then we get the button we do not press, so we may as well just ignore that exists. Moving down along the board, we find the clear Cmos jumper as well as the front panel headers. Also some, troubleshooting LEDs over there, just your usual VGA, CPU, boot device, and memory error indicators. The front panel header is color-coded, which is kind of neat. That's kind of a nice thing that Gigabyte does. We have a reset button here. There's no power button or clear CMOS button on the motherboard, but there is a reset button. Then next to that we have a postcode, so that makes these completely redundant, because this obviously gives you much more detailed information about any kind of boot errors you may be having. So this is really nice to have. Then along the bottom edge, we have the feature, the feature solving a problem that Gigabyte created. So Gigabyte motherboards, pretty much all of them, as far as I'm aware, I think actually all of them, but I don't want to say definitely all of them, because I don't go, I don't generally check all the low-end stuff, and maybe there's one board where they don't have it. But generally speaking, Gigabyte motherboards have dual BIOS. And this is great, because that means if you break one of your BIOSes, you have a backup BIOS, so you can fix the broken BIOS from the backup BIOS, right? Your motherboard doesn't instantly turn into a brick if, let's say, your power goes out while you're flashing the BIOS. Or you do something very stupid, like trying to flash the BIOS with an unstable CPU overclock and the system crashes midway through the flash. There's a bunch of ways to basically screw up a BIOS flash. So, you know, it's nice to have the backup BIOS to recover from that scenario. However, the dual BIOS system on Gigabyte motherboards is a little bit overly aggressive. And by that, I mean it tends to kick in even if you just have bad overclock settings. So not an actually corrupted BIOS. It's just like if you fail to boot a few times in a specific way, the board will randomly decide to switch you over to the backup BIOS. And then when that one fails to boot a few times, it'll throw you back onto the main BIOS. And this gets really, really annoying very, very fast because the issue with this is that every time this happens, you lose your profiles because the profiles are tied to whichever BIOS chip you're on. So if you save, let's say, 3 overclocking profiles on the main BIOS chip, and then you proceed to fail, you know, to boot a couple times and you get thrown onto the backup BIOS chip, well, you're going to have to make those 3 profiles again. And then, you know, eventually you're going to get thrown back to the main BIOS chip and you keep going back and forth. And so Gigabyte on their high-end, more expensive motherboards, motherboards targeted at overclocking, they include the single BIOS mode switch and the BIOS select switch. So this switch allows you to choose which BIOS you're actually on. And this switch disables the automatic software system that Gigabyte has for their dual BIOS system. So this is super handy if you're actually doing like serious overclocking on a motherboard. Now, obviously, there is a way to work around the profile situation on the cheaper boards without these. You just plug in a USB stick and just use that USB stick to store all your profiles. Or you can use a hard drive as well, but I generally use a USB stick. I have like one USB stick just dedicated to, you know, BIOS profiles for various motherboards. So if I run into a motherboard that's especially stupid, I don't have to, you know, deal with it losing the profiles all the time. So that's kind of that. And anyway, moving on from the switches, we finally get to the power and clear CMOS, which are in the wrong well, one of them's in the right place and the other one's in like the worst possible location. So this top switch is power. The lower switch is clear CMOS. This is dumb. Okay, just putting them next to each other on the rear I/O like this is completely freaking stupid. Putting the clear CMOS on the rear I/O is good because, you know, if you have the motherboard in a case, and you screw up and you need to clear CMOS, well, you can just go and hit the button. It's on the rear I/O. You don't need to open up the computer to get at the clear CMOS jumper, which is great. But having the power button on the rear I/O is completely stupid because the only time the rear I/O is more convenient to access than like we're like, this is a power button integrated to the motherboard. So this is for like test bench usage. The only time the rear I/O is more convenient to access than like all of the rest of the motherboard is when the motherboard is in a case. If it's on a test bench, you know, I don't know. I want to see the postcode, so I'll probably have the postcode relatively near to where I'm sitting. So it would be probably kind of nice to have the power button somewhere near the postcode. I get that they have a whole bunch of crap down here, but like there's space here. There's this thing that doesn't necessarily need to exist as far as I'm concerned. But really there is a bunch of space right there. It's like, you could have put the power button there. I don't think that's the best place to put it either, but it would have been a lot better than, you know, putting it here. Especially when it's right above a clear CMOS button, because then it's just like, oh yeah, you're gonna try. Like, I don't think it's too much of a risk, but you might reach there. You know, you might press a button and you might hit the clear CMOS at the same time by accident, and then that's gonna suck. So I am really not a fan of having the power button on the rear I/O. It's just like, it completely defeats the purpose of having a power button on the motherboard. And this is true because I have this motherboard on my test bench right now, and I've actually plugged in the front panel connector because that power button is as far away from me as it can get on the test bench. Like, that's just how I have my test benches always set up. There's no way I'm going to reach that. At least not conveniently. I don't mind the clear CMOS. I don't need that functionality that often, but the power button is in the wrong bloody place. Anyway, so that kind of covers all of the you know, top level features or whatever features I wanted to highlight about this motherboard. Now let's get into the VRM. V-Core VRM is where you'd normally expect it to be on an Intel motherboard in the usual Intel motherboard layout. So it's this lovely L shape right here, and so that's our V-Core. And then next to that, we have the iGPU power, of course. So that's iGPU. Whoa, my letters look really great today. Um, and for the V-core, we have a 1, 2, 3, 4, 5, 6, 7. That doesn't look like a 7. That's a 7. 8, 9, 10, 11, 12 phase VRM. And this is actually like, well, about as real 12 phases as you can get, because obviously nobody currently makes a 12-phase voltage controller. They do make 10s, but, you know, that's still not enough. So the way Gigabyte is getting their 12-phase setup here is with IR3599 doublers, which are a bit dumb. They don't include any kind of current balancing capabilities, but they can also quadruple. So if for some reason Gigabyte wanted to do a 24-phase, they can just keep using these. And a 6-phase voltage controller. And ultimately, the controller here sees this 12-phase setup as a 6-phase plus 2, and the plus 2 is, of course, for your 2 iGPU phases over there, and the controller is the ever so popular IR35201. Very common on high-end motherboards. The only other competitor it has is the ISL 69138 right now. So, yeah, that's the setup right here. IR35201, IR3599s for the doubling, and ultimately you get 12 phases. And they are fully interleaved because of the 3599s, so you get the output ripple reduction, the input ripple reduction. However, you don't get full current balancing because as far as the IR35201 is concerned, these are in groups of 2. Like they're not separate phases. So that's basically what's going on with that. Now, what do we have? We have the control scheme. Oh yeah, I did want to mention that Gigabyte does actually allow you to adjust the VRM switching frequency on the motherboard. The adjustment range, though, is kind of as they allow you to tweak it from 300 to 500 kilohertz, which is nowhere near the full range of this chip or these power stages. Now, I'm not sure if they're specifying this as 500 kilohertz on the actual phases. I think they are, because otherwise otherwise they'd be getting like 250 kilohertz after the 3599s, even with this completely maxed out, and the motherboard ships at a switching frequency of 400 kilohertz stock. And you literally just have 3 settings, like you can do 300, 400, or 500. So I'm kind of sad that, you know, it's just like this chip goes all the way to 2 megahertz, and assuming this is post doubler frequency, that would translate into like this 500 kilohertz setting is like 1 megahertz on the actual 35201. As I've said, I've yet to actually check that, but I assume that's how the BIOS is working, because really the 35201s, like they do not gain a whole lot of efficiency by running them really, really slow. It doesn't really make a whole lot of difference. So I don't think it's reasonable to run them below that 400 kilohertz frequency anyway. But and then the actual, like, the chips right here are IR3553s, Gigabyte's favorite power stage. And actually, I'm not going to have enough space up there, so let's do it somewhere else. So the other component as far as the switching frequency goes is, of course, the Mosfets themselves, and that's the 3553, Gigabyte's favorite power stage. It's rated for 40 amps maximum output, and it supports a maximum switching frequency of up to 1 megahertz. So they could have totally maxed out that 2 megahertz capability of the 35201. Like, they totally could have done that. Now, admittedly, at 1 megahertz, these things get really inefficient. But I don't know. It's just like ultimately, I don't think you're actually, like, I'm going to definitely test if this actually makes a difference. I have very little, I really don't think it will. With the 9900K, that, like, cranking up the switching frequency will make any difference. Hell, it might be best to just run the motherboard at 300 kilohertz to get better VRM efficiency. But yeah, as far as, like, it's just kind of like, well, like MSI has a motherboard where you can set the switching frequency all the way up to like 9, like MSI, when they do give you switching frequency controls, like I think I have one board that goes all the way up to like 1.2 megahertz. I have another board that goes to like 900 kilohertz, and it's just like they give you the freedom to potentially just break the VRM if you feel like it. And it's just, well, not necessarily break it, because they do like cap you at what the chips are capable of supporting, but they, you know, they don't worry about you setting the VRM into switching frequencies, at which point they are really, really inefficient. It's just kind of like, yeah, do whatever. If it overheats, we have over temperature protection. It'll kick in early enough, hopefully. So yeah, I think like I don't think it matters, but it's just kind of like I wished we had more range on that. I think it would have been cool to be able to, you know, test up to like a megahertz and find out that, yeah, going all the way up to a megahertz is completely pointless with absolute certainty. Anyway, let's talk VRM efficiency. Now, I am not actually a big fan of this VRM right here. It is a 12-phase, it is using 40 amp power stages, but the thing is, Gigabyte has another 12-phase VRM that they use on their cheaper boards, which on paper is better. And I say on paper because I actually talked to Gigabyte about this. I was like, you do I basically said the 50 amp power stages you use on your cheaper motherboards, according to their data sheet, are just way more efficient than these things, than the IR3553s here. And the response I got from Gigabyte was like, yeah, but we tested these and these run cooler. Like, ultimately, apparently, this VRM runs cooler. Now, luckily, Gigabyte did send me one of these motherboards, and they also sent me a Z390 Pro, and that does use the 12-phase VRM using the 50 amp power stages. So we can actually compare both designs to see which one ultimately is more, you know, runs cooler and is potentially more efficient, which I gonna have to figure out some way to figure out some way to measure that, because that's gonna be a bit fiddly. But on paper, this VRM kind of sucks, is just like what I'm going to start with. And, you know, as we get into the efficiency numbers, it's still better, I think, than pretty much all of the other motherboards at the same price point. It's just like, on paper, the boards from Gigabyte that are cheaper than this are better than this. However, you know, at the same time, theory and practice are only the same in theory, so I'm willing to you know, accept that, hey, maybe the paper the on paper values aren't actually reflecting reality accurately. Anyway, operating parameters for this VRM here are going to be 400 kilohertz switching frequency, 5 volts drive. I've asked Gigabyte about this, and apparently, like, the funny thing is the IR3553 datasheet is entirely spec'd at like 7 volts, but apparently there's reliability issues with these chips if you run them at 7 volts. And unfortunately, according to the datasheet, they get really like a lot less efficient if you run them on 5 volts than if you run them on 7 volts. So that further just like these aren't great when they're on 7 volts. They're even worse when you put them on 5 volts. Now, they still work out to not be completely terrible, but it's just, yeah, like the numbers here are not going to be impressive compared to, say, like when we do the other cheaper boards, like the other VRM from Gigabyte. Now, 5 volts drive, 1.3 volts out, and in my desperate, you know, search for some way to figure out why these things would be more efficient than the other chips, these do actually get more efficient as you increase your output in like the inductance of your output inductors. And now Gigabyte doesn't actually use 210 nanohenries. These are all 300 nanohenries. But the thing is, the efficiency scaling curve, well, the power dissipation scaling curve from International Rectifier in the datasheet ends at 210 nanohenries. And I don't know how it continues past that. It basically starts to level off at that point. Kind of looks like that. So, well, not quite like that, but it's more mild. So, yeah, and basically at this point is 210, right? And so I don't really want to like extrapolate too much and say that 300 nanohenries is going to further improve the efficiency a bunch, because I don't know. The data sheet doesn't specify, and there's nothing really there that I could use to calculate that kind of thing. But if we just go with these parameters, like this is as close as what the VRM is probably doing in reality. So then at these you know, operating parameters, at 150 amps output, this VRM will produce about 19.5 watts of heat. And yeah, that's that's not ideal already, but it is a 12-phase. It does spread all of that heat across a very large surface area, and so it should have no problem dealing with that. Now, when we go up to 200 amps output, The power consumption, the efficiency actually doesn't change that much because I think, honestly, I should have probably calculated the 150 amp figure for a lower phase count than 12 because I have a sneaking suspicion they're outside the peak of the efficiency curve for this. This is just too little current going through these, or might be, or it might just be that running them on 5 volts is just terrible. One of the two. But anyway, so 200 amps output, you hit 25 watts, which is better than the ASRock Taichi. It is also better than the Asus Maximus 11 Hero motherboard. The only issue is, like, it's just not exactly incredible. That is really not a, like, let's just put it this way. When we get to that other 12 phase, we're going to be looking more at, like, 20 watts for 200 amps output instead of 25. Now, in terms of actual cooling capability, like, the VRM is not going to have a problem dissipating that. There's, like, this is, it is spread across 12 phases, so it's not a huge, like, it's relatively low thermal density, but nonetheless, like, this is not a incredible efficiency figure. It would be a lot better if these ran on 7 volts, but again, like, Gigabyte told me that apparently there's reliability issues doing that, and if they did run them on 7 volts, we'd be looking more at, like, 22 watts. Instead of 25, but that's just, yeah, they run it on 5 volts, so this is what the paper says, and the paper might be wrong, and that's why I intend to test this, right? So anyway, moving on, 250 amps, which at this point we're very much starting to enter theoretical territory. A 9900K is going to need close to 1.4 volts to push 200 amps out, to pull 200 amps from the VRM. And at that amount of voltage, at that voltage and that amount of current, the CPU is also going to be producing so much heat that it's going to be pretty much uncoolable unless you have it delidded with probably a sanded down die and liquid metal. So practically speaking, you're going to be looking at the VRM running below that 200 amp output figure. And that 150 amp figure is more for like an 8700K or a 9700K, as they, funnily enough, hyper-threading adds about as much power consumption as it adds performance, and 8 cores is about 33% more cores than, 6 cores. So, well, 8 cores is exactly like 33.333% more cores than, 6 cores. And funnily enough, hyper-threading adds about 30 to 40% more performance and also about 30 to 40% more heat. So the 9700K and 8700K both fall into the 150 amp category. Again, depending on your cooling capabilities, 9900K goes beyond that towards the 200 amp range. 250 amps, we're starting to enter theoretical territory. I think it might be possible on various subambient cooling methods to hit that at very high voltages. But the thing is also subambient cooling also tends to improve your CPU's leakage, and that actually improves your CPU's efficiency, which reduces the amount of current it needs for any given voltage. So the current, like, the power consumption doesn't get quite as bad as you'd expect it to when you go on LN2. So anyway, 250 amps output, this VRM would be producing about 35 watts of heat, which is quite a bit of heat. But again, if you have substantial enough heat sinks, this should be doable, as you have because it is, again, still spread across 12 phases total, right? So there's a lot of surface, like it's not very high density in terms of thermal dissipation. Now, going up to 300 amps, and this is where the VRM really starts just kind of lacking. Like, this is a problem with the 3553, is just, like, if you put a pile of them, they tend to not do as well as if you used fewer higher current rated power stages. Just like, if you just compare their efficiency curves, these things have a peak efficiency that's just lower than a lot of the higher spec power stages, like the 50 amp parts and the 60 amp parts. Like 60 amp parts can regularly do like 94.5% efficiency or better. These top out at 93.2%. Like, that is their absolute peak efficiency. And the end result is that, as you keep cranking up the current, it starts these start steadily losing more and more to lower phase counts with higher quality components. So while in this range they're just fine, 300 amps, they're starting to show the weaknesses, and we hit 47.5 watts of heat output, which with airflow, I'm pretty sure you could still deal with that. And this is very much completely theoretical. Like a 9900K should not be able to hit that. 350 amps output, which at this point we're in the numbers that I do just for fun to see, you know, how unreasonable the heat output of the VRM could get. 350 amps output, you're going to be looking at about 62 watts of heat. And finally, 400 amps output, you're going to be looking at 81 watts of heat. This is not the most efficient VRM on Z390. But Gigabyte does say that, you know, it runs cooler than the VRM they have for the cheaper boards than this, even though that VRM is on paper more efficient. So I do intend to test that. Of course, the way I'm going to be testing that is by taking off the heatsinks, like running the motherboard with no heatsinks, because the heatsinks would obviously skew the result in favor of the motherboard with the bigger heatsink instead of the motherboard with the more efficient VRM. And then I'll try figure out some way to actually measure VRM efficiency, though that's really hard because it's easy to measure the power going in. It's really hard to get like a reliable, like it's hard to match up the input power with the output power, right? If you're measuring with two different systems. So we'll see if I actually get anywhere with that, but just a thermal test with no heat sinks, I can definitely do that. And I'm definitely going to be doing that just because I find it really hard to believe that these are beating the 50 amp Vishay semiconductor power stages that Gigabyte has on their cheaper motherboards. So yeah, like that is just something I'm going to test. And if it does, you know, if these do win, then I guess the Vishay semiconductor data sheet isn't quite as like one of the data sheets is obviously not exactly accurate, would be one way to put it. Because, yeah, unless there's some kind of, like, heat dissipation difference between the PCB designs, but that shouldn't play too much of a major role. Anyway, moving on from the V-Core VRM, which I think it's fine. It's just, you know, it's not the most efficient thing ever. And, like, definitely on paper, this is not an amazing design, but we'll see. We'll have to see in testing. Now, for the iGPU, the Gigabyte's using the usual 4C10N high side MOSFET and the 4C06s for the low side. These, like, I don't like these MOSFETs. This one's pretty bad. This one's, well, this one as a high side is fine. This one as a low side kind of sucks. But this is for iGPU power. You're not going to be stressing that VRM a whole lot, so I don't really see a problem with them being used right there. It's just that Gigabyte has a tendency to also use these things and say, like, V-Core power on their really, really cheap motherboards and in very low quantities, and then I have a problem with those. So, yeah, they're not the most efficient things, but, you know, just iGPU power, they're not going to have a problem with that. Now then, here we have the, what I assume top one's going to be VCCSA, just because that's the usual layout, and the lower one is going to be VCC IO. And for this is, both of them are single phase, you know, just one phase right there. That's the actual that's the actual voltage regulator in there. This is just input filtering to just block out the switching noise from the high side MOSFET, basically, you know, switching on and off. So that's there just to filter that out. And the voltage controllers are these two chips right here. And I assume they're still like I've not actually checked this board, but they're probably the same RT8120s that Gigabyte uses on their other motherboards. And I think it's that part number. I unfortunately didn't bother to write it down, but it's a Rich Tech single phase voltage controller that Gigabyte just kind of uses everywhere. So I don't see an issue with that. And I might have the part number wrong, so do keep that in mind. Over here, we have a bunch of linear regulators for our various extreme overclocking voltages like VCC-PL-LOC, VCC-PLL, VCC-VTT, VCC, I think it might be just called straight DMI, or it might be VCC-DMI, but it's it's related to the DMI interface. Well, I think that's redundant, isn't it? Because DMI, the I stands for interface. Anyway, there's DMI voltage here. And all of the various, like, all of the necessary extreme overclocking voltages are available on this motherboard. Though, talking to Gigabyte about how they're implemented, these don't actually kick in until after the motherboard has booted. So while the motherboard can remove a cold bug, it can't actually, like, cold boot. As in, if you try to run this if you try to restart this motherboard at like minus 150 degree, like below minus 120, it's not going to restart. But once you have it running, you can set up your voltages, and then you should be able to pull it all the way down to like minus 190, no problem. So it can overclock on liquid nitrogen. Lucky Noob has already posted some scores using this motherboard. I think he got like 6.6 gigahertz on a 9900K with it. I don't know how much time he spent doing that. I don't know, how many like if that was the best chip he had, or if it was just quick testing, or like it. But the board can run on LN2. Just we'll see how well. The like everything is here. It's just, not quite as it's not fully implemented. Gigabyte kind of doesn't do really extreme overclocking focused motherboards, but at least this board can kind of do it, which is nice. Like I think that's kind of good enough in a lot of ways. There's also a clock gen right here for your extended BCLK range, as well as better BCLK control just overall. Memory power is a single phase right here, which is, if I'm not mistaken, that's a 4C06 high side, and I have checked those. And yeah, that's a 4C06 everything. And then you have a 4C06 low, and then you have actually two 4C06 and low sides, and yeah, so just both of these are the same chip right there. And that's your memory power. It's a single phase controlled by that same Richtech voltage controller. Gigabyte has a maximum voltage limit of about 2 volts. They also, what's kind of neat on Gigabyte motherboards is they actually have a training voltage. So you can actually set you can set a memory boot voltage, and then you can have a memory running voltage. So you can boot up at like 1.8 volts and then run at 2 volts. And in some scenarios, that can actually help you pass memory training to train at a lower voltage and then run at a higher one. You kind of need to mess around with that to figure out if that's actually worth doing, but Gigabyte does have the option. I do think the 2 volt limit is a bit low for like a motherboard that's supposed to kind of do everything, right? Because we do have the voltage read points, we have a solid VRM, we have the necessary voltages for extreme overclocking, we have the BIOS switches to get rid of the silly BIOS, we have the postcode, we have like almost everything. Voltage limit is a bit low. But you can still go pretty far on 2 volts as long as you have a good kit of memory. Memory layout, being a 4-DIMM motherboard from Gigabyte, this is still on T topology. And I've used a motherboard that uses a similar layout. Like, I've not yet tested this motherboard for memory overclocking, but at least on the Z390 Gaming 7, about 3800 CL12 for me works fine. 4000 megahertz CL12 would boot, but I could never get it stable. Partly because my RAM needs a lot more than 2 volts, and partly because, I think actually it's probably mostly because of the 2 volts limitation. So, yeah, but the memory layout here is really, like, the thing about T topology is it's really optimized for running 4 memory sticks, not just 2. So, yeah, again, like, this motherboard just tries to kind of do everything. And for a daily system, I think that's great, right? Like, this motherboard has pretty much everything you'd ever want. And then if for some reason you decided that you wanted to get into extreme overclocking and you upgraded your daily system and you no longer have a use for your previous one, well, you can take this motherboard on LN2 and it'll kind of work. It's just that, yeah, it's not going to keep up with, like, the various 2-DIMM motherboards because there's way too many memory slots, and they're also wired for 4 memory sticks instead of 2. And also just, VRM is fine. It's just, like, these voltages don't get applied at boot, and that's really the biggest issue. So, that's really, like, the biggest issue for extreme overclocking. So, yeah, overall, like, for a daily system, I don't think there's really a better balanced motherboard, because you do kind of get a little bit of everything, and you do get a, like, solid, really solid 12-phase VRM, which we still need to test. Like, it's not the most efficient. Again, I still think the cheaper boards from Gigabyte should be more efficient than this, at least according to their according to the data sheets for those power stages, but if those aren't more efficient, then this is probably the most efficient VRM on Z390, other than, like, the ultra high-end motherboards. Yeah, you have voltage read points, you have postcodes, you have single BIOS mode, you have, like, there's not really, like, if Gigabyte went and just built this motherboard again with 2 memory slots less, I would be perfectly happy using that, like, just, you know, running that on LN2. Also, if they got the voltages to apply at boot up instead of after boot up. But if you just axed 2 of the memory slots, I'd be, you know, perfectly happy with it. So, yeah, I like the board a lot. It's just kind of I don't know. It kind of tries to do a little bit of everything. And it does, I like the end result for a daily system. It's great. It's just in extreme overclocking, it'll kind of not work out that well because you can't have 4 memory slots. You just can't. It's terrible for memory overclocking support. So, yeah, that is it for the video. Thank you for watching. Like, share, subscribe, and oh my god, this one's long again. Well, there's a lot to cover on a motherboard like this. This thing's really loaded with stuff. So, yeah, thanks for watching, and like, share, subscribe. I don't think I've said that yet. And if you'd like to support what I do here with the channel, I do have a Patreon and t-shirts. You can support, so you can, you know, find links to both of those down in the description below. And what else did I want to say? Oh, yeah, and, you know, thank you to Gigabyte for actually sending over one of these boards for testing. I've still yet to get around to doing that, but it is on the test bench, and I've booted it up like once or twice. So, yeah. You know, I will have more information, like more real-world testing information on this motherboard in the future. But just looking at the PCB, I like what I'm seeing a lot. So, yeah, that is it for the video, and goodbye.